Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the 7th chapter of microwave engineering, where the microwave transmission lines we are analyzing. We started to take the help of a circuit model that involved the lumped elements R, L, G and C with respect to per unit length I can say here. We have also found the solution to the microwave transmission line equations for the voltage and the current form. So after that we had the knowledge of reflection coefficient, the transmission coefficient, standing wave and the standing wave ratio. For these topics also we have solved few of the sample problems, and then we have moved to see what exactly the line impedance or the line admittance corresponding to microwave transmission line is. Now in this video we are going to start with a very popular method, which is a graphical one called as Smith chart, to find the solutions and the certain parameters with respect to microwave transmission line. So let us begin with. So here we start with our topic. The topic is titled Smith chart. So now what is the purpose to have the Smith chart into the use for microwave applications or microwave engineering subject we can say. So this is to solve transmission line problems. Now there may be one question into your mind that when the Smith chart is going to use for solving the transmission line problems, what was the use of earlier topics that we have gone through with rigorous derivations and formulations of certain parameters of measurement. So this is all the knowledge that we have gathered to understand the behavior of microwave transmission line, and Smith chart is nothing but a graphical method. In this graphical method, such a Smith chart, which is developed by the scientist named Philip H. Smith here, hence the name of the chart given by him is called as Smith chart. This is a graphical method, and on this such a graph or a chart you can see here the various parameters that we have studied up till now with respect to the microwave transmission line. The ranges of those particular parameters have already been there on this particular chart. So this graphical method is arriving at the solution for the problems of transmission line at a quick answer. So at quick, so it is giving us the answer with very few steps. A fast answer can be determined with the help of Smith chart. That is why it is very popular in the domain to solve the transmission line problems. Now what is there inside the Smith chart? The Smith chart consists of the normalized impedance or the normalized admittance we can say. So as the previous topic we have gone through, that is line impedance and admittance, here at the last we can express the impedance into the normalized form, and also we can go for the normalized form of the admittance. So it is plotted into the Smith chart there. Further, the chart is having the information in the form of angle and magnitude for the reflection coefficient. The reflection coefficient, we know that the reflection coefficient can be denoted with the capital gamma sign here. Now most of the time we find the values of reflection coefficient into the complex domain. So in the Smith chart we have the complex representation of the values. So the complex representation involves the real part and that of the imaginary part also. This is the generalized representation, not exactly the attenuation coefficient and that of the phase shift coefficient here. So the real part and the imaginary part both are plotted inside the Smith chart there. Now addition to this particular one, a simple rotation of the chart can give us the effective position the effective position onto the transmission line where we are making the measurements performed there. Now, as we know that the reflection coefficient for the transmission line we have represented corresponding to the load, here we represent gamma suffix L. So it is in the form of load impedance ZL minus characteristic impedance Z0 divided by the addition of the two here. So this can further be expressed as the magnitude represented the mod of gamma suffix L into, here we have e to the power j times theta suffix t here, or we can split it in the form of real part and the imaginary part as represented gamma suffix r for the real portion added with j times gamma suffix I to represent the imaginary part here. So here this representation of the reflection coefficient we can regard as equation number 1 in our topic. Now for the reflection coefficient, as we know that the mod of reflection coefficient is never greater than unity, it is always less than or equal to 1. The value must be lying within the unity circle there. The Smith chart we shall be definitely discussing with how the appearance of the Smith chart is. I must tell you it is having these circles there plotted corresponding to the pure type of the resistance as well as the reactance type. The combination of the two is nothing but the Smith chart we shall be seeing. So here this condition is very important. So here the reflection coefficient value will be within the unity circle. We can say the unity is the maximum possible value for the reflection coefficient corresponding to the transmission line under consideration there. Next to that, the reflection coefficient, this we have represented suffix L corresponding to the load position here we can say. Now at any position onto the transmission line, when we are going to determine the reflection coefficient, we denote it as gamma suffix small d. So gamma suffix small d is equal to gamma suffix L represented earlier in multiplication to the exponential e to the power minus twice alpha times d into e to the power minus j times twice beta into d here. So this gives us the form of the equation as mod of gamma suffix L into, here we have e to the power minus twice alpha into d into e to the power j times in the bracket theta suffix L minus twice beta suffix d here. So let this can be regarded as equation number 2 for gamma suffix d here. So in this equation, the reflection coefficient at any point onto the transmission line is also within or onto the unity circle. Now let us go through one figure that gives us this information. So see, in this schematic we have the use of the two axes where the horizontal axis is giving us gamma suffix r as we have represented into the earlier equation for the real part of the reflection coefficient, whereas gamma suffix I is giving us the information of imaginary portion of it. Now here we have the different circles here. The reflection coefficient at its maximum value mod of gamma is equal to 1 is the outermost circle here we have, and inside thereupon we have another circles with the values of gamma to be less than 1 here. Now along with this particular plot we have the information represented for this certain point marked here in this plot, which makes the angle theta suffix L with the real axis represented here. Now if we go for the another point location inside this particular unity region of the circle, we can say here we get the angle measured like this corresponding to this gamma suffix L as theta suffix L, the angle earlier measured, minus twice beta d here. So this is the point of beta d, beta representing the phase shift constant and d is the location onto the transmission line here. So the schematic that we have discussed here is for the constant gamma circles, gamma representing the reflection coefficient. Along with, here we have the electrical length radials for beta suffix d, we can say here. So these are the two informations, that gamma circles and the electrical length radials, that have been combined in this particular schematic. Now, as we talked about the Smith chart, that is very helpful in determination of the impedance at any location, we can express the normalized type of the impedance and the normalized type of the admittance here. So very first of all, we shall mention the equation related to that of normalized form of the line impedance, I can say here. So the normalized line impedance is represented by small z. It is the ratio of capital Z divided by capital Z suffix 0, the characteristic impedance. So it is in the terms of the numerator having 1 plus, we have gamma suffix L into e to the power minus twice gamma d, whereas the denominator is 1 minus gamma suffix L e to the power minus twice gamma into d here. Let this can be regarded as the next equation, equation number 3. In continuation, we expect that there it is no loss in the general case, and it is assumed that the d value will be equal to 0. So in that particular case, the normalized impedance small z can be simply expressed as 1 plus gamma suffix d divided by 1 plus gamma suffix d. As d we substitute to be equal to 0, we go for the entire length of the microwave transmission line. So it becomes 1 plus gamma suffix L divided by, we have negative sign to the denominator. So here we have 1 minus gamma suffix L. So here also we should be preferring the negative sign instead of the positive here. So now we continue further for this one. To represent the normalized impedance, we can be having it the ratio of the load impedance divided by the characteristic impedance Z0 here. As we approach d is equal to 0, we are at the load position, hence we substitute the numerator to be Z suffix L here. Now for the normalized impedance that we have represented small z here, we can separate out the representation into the real and imaginary components for the complex representation here. So therefore, as we have the numerator, the load impedance here, it can be expressed into the real and imaginary portion. So we express small z is equal to capital R suffix L. So this is added with, we have j times xl here, and divided by, we keep Z suffix 0 as the characteristic impedance, the real portion. So this can be regarded as small r added with j times small x, the real and the imaginary parts here. So let this can be the representation of normalized impedance by equation number 4 here. Along with, we can express gamma suffix L is equal to, in the form of normalized impedance, Z minus 1 divided by Z plus 1, which is equal to gamma suffix R added with J times gamma suffix I here. So the real part of the reflection coefficient and the imaginary part of the reflection coefficient. So let us represent it by the new equation, equation number 5 here. Now when we have solution of this equation number 5 into the equation number 4, so that time we obtain small r value and small x here. So small r is given by 1 minus gamma suffix r square minus gamma suffix I square. So this is the mathematical relationship between the two in the numerator, whereas the denominator is given as 1 minus gamma suffix r, it is bracket squared, and added with gamma suffix I squared here. So let this can be the equation number 6. Whereas the another component small x is expressed as we have twice of gamma suffix I divided by, in the bracket we have 1 minus gamma suffix r, bracket is squared, and it is further added with gamma suffix I squared here. So this can be the next equation, equation number 7. Now if we have the equation number 6 before that for the component of r here, and this equation number 7, we can make the rearrangement as, let us say, the left hand side is represented by gamma suffix r minus r divided by 1 plus r, and it is squared here, and further it is added to gamma suffix I squared. It will be 1 upon 1 plus r bracket squared. Let it is equation number 8. And the further rearrangement can be in the form where we have gamma suffix r minus 1 bracket is squared here, added with we have gamma suffix I minus 1 by x bracket squared is equal to 1 by x bracket squared here. Let it is equation number 9 here. So now when we have a look onto the equation number 8, the form of the equation for this equation number 8 is of the equation of circle here. So we can say in general that the equation number 8 is giving us a family of constant circles. For the family of constant circles, we have the resistance represented by r here. So as it is completely a real part, we can say r is nothing but the resistance here, and for the circular shape here, we have the radius of the circle represented by 1 divided by 1 plus r here, whereas the center of the circle is at r divided by 1 plus r here. Now along the real axis of the unity circle, we have this particular center where r varies from 0 to infinity. So r is equal to 0 to infinity, corresponding to the information that we express in graphical form from this equation number 8 here. Now all the constant resistance R circles that can be plotted, we see with the help of one diagram. This is the diagram. This diagram we can regard as constant resistance denoted by small r circles here. So as discussed, we have the center for r is equal to 1 in this particular plot. So this is the unity circle, we can say r is equal to 1. When we go for r is equal to 2, we obtain a smaller circle. Then r is equal to 0.5, when we take, we get such a circle for r is equal to 0.4, and r is equal to 0 we have plot in this particular graph here. So in this graph, the real axis is representing the real part of the reflection coefficient gamma suffix r, whereas the imaginary part is represented as gamma suffix I here. We see here onto the left hand side of this diagram where we have constant resistance R circles. 0 is onto the left, the smallest possible value, and it is extending up to infinity for the resistance value R here. Whereas the center of the graph we have obtained at R is equal to 1, which is having a pass for this unity circle here. So now when we look at the next equation, equation number 9, the equation number 9 is also giving us the form of the equation for circle. So the equation number 9 is also expressing the information for the constant circles, but this time for the x here. So x is nothing but the reactance value here. R is the pure resistance, x is the reactance value, and for the x of circles here we have the radiance represented by 1 upon x here. So here 1 upon x that has been squared is nothing but the radius of the reactance circles that we can plot with the help of this particular equation. The center for this particular graph will be at gamma suffix r is equal to 1, gamma suffix I is equal to 1 by x, where we have this x within the range of minus infinity to x up to the plus infinity here. So the x lies between minus infinity to plus infinity, whereas r lies between 0 to the positive infinity. So let us take the diagram to see the details of this equation number 9 for the constant reactance circles. So this is the diagram. We can make nomenclature that it is constant reactance x representing the reactance in this case, and these are the circles of constant radius here. So in this particular plot we have the real part of the reflection coefficient denoted in the horizontal axis, the imaginary part onto the vertical axis intersecting at the point. This is the center. We have represented 1 here. So initially we have 0 to infinity. From the previous schematic we have discussed for the pure type of the resistance, and now we have these circles. So these circles are originating at this particular point, we can say here, and here we have the positive values towards the upper part here, whereas the negative values towards the lower part here. So these two completes the circle here. We have here 2.0, 2.0, but this 2.0 corresponds to the positive jx here, whereas this 2.0 corresponds to the negative jx. Similar is the case for the upper part, positive 1.0, for the lower part negative 1.0. Here we have the positive 0.5, here we have the negative 0.5, and this is the zero line, we can say, that separates out the positive and the negative portions of the imaginary representing the constant reactance circles here. So here we have represented 1 by x to show the corresponding measures of radius for the constant reactance circles in this particular schematic diagram. Now just now we have discussed about the constant resistance R circles and the constant reactance X circles here. Now when we get both the circles combined, so this combined form of the constant circles for corresponding X and R here gives us the relative distance in the form of scales corresponding to the wavelengths represented by lambda along the circumference of the circles here that we have for the constant resistance and for the constant reactance onto the Smith chart. So Smith chart is the combined form of the plot of constant resistance and constant reactance circles that we shall be seeing here. So as like the relative distance, the Smith chart also gives us the information related to that of the phase here. So the phase will be specifying the information in terms of the angle that we usually denote it by theta here. Now when we have the normalized impedance denoted by small z here, the normalized impedance, when it is plotted over the chart, we can determine the normalized impedance at any of the location onto the transmission line. So this can be found by use of the equation z is equal to, we have 1 plus gamma suffix l into e to the power minus j times 2 gamma d here, where we have the denominator 1 minus gamma suffix l e to the power, we have minus twice gamma d here. Now in this equation we have gamma suffix l into e to the power minus twice gamma d is equal to mod of this reflection coefficient gamma suffix l into e to the power minus twice alpha d into e to the power j times theta suffix l minus twice of beta into d here. So these two equations can be regarded as the next ones, and now the Smith chart may also be used in the terms of normalized admittance. Only the difference we need to make is that the characteristic admittance y0 is the reciprocal of the characteristic impedance z0, which can be further expressed as the addition of g suffix 0 plus g times b0 here, and capital Y is equal to 1 by Z in general. This is not the characteristic condition. So in general we have it is the addition of G plus J times capital B here. The normalized admittance can be represented by small y, and it is equal to capital Y by capital Y0 equal to capital Z by 0 by capital Z equal to 1 upon the normalized impedance small z is equal to, in the small case we have G added with J times small b. So this is in the terms of admittance parameters we can say for the Smith chart. Now let us have the complete Smith chart displayed, the combination of the constant resistance circles and the constant reactance circles here. So here this is the Smith chart. Here in this particular Smith chart we see the various details where the wavelength towards the generator has been marked in this particular direction. We start at the 0 value and the values as like 0 0.04, 0 0.05, 0 0.06 we go on increasing in this particular direction. Whereas we have the markings of wavelength towards the load in the reverse direction. So we come to know that we have a generator on this particular side, the load on this particular side. So along with the information with respect to the wavelength scales here towards the generator and towards the load. So generator is the source side, load is the other end side where the application is to be delivered by the input power here. So now along with the wavelength scales we have also the information regarding the angle of reflection coefficient in the degrees here. So here it is the marking with very small writings here. It is all the information accommodated into the Smith chart here. Here also we have the angle of transmission coefficient in terms of degrees below to the information of that of reflection coefficient. So from the knowledge of one coefficient we can go to have the computations of the another coefficients here. As we see for the circular type of this particular chart, this is the center, and for this center we have the marking 1.0 as stated before here. So in this particular Smith chart we have the resistance comment given by R divided by Z0, or the conductance component here given by G divided by Y suffix 0 here. We have the inductance components on the upper side here. So it is basically the positive portion of the imaginary part here, whereas we have the capacitive reactance components on this particular portion, which are nothing but designated by minus J of the imaginary components here. So here we have the wavelength scales, the reflection coefficients into the degrees, the transmission coefficient into the degrees, the real part on the middle line extending like this, right from 0 to that of the infinity, whereas the center is the 1, and this is for the positive imaginary components in the form of inductive components, and this is for the negative imaginary portion for the capacitive components here. So along with we have these particular scales, these are basically the radially scaled parameters. So we have the directions towards the load, towards the generator again, whereas the center is marked here. So we can have the information for some more parameters of the transmission line as like the SWR here, the standing wave ratio that we usually represent by the symbol rho here. See, the attenuation can also be measured in the terms of decibels with the help of the Smith chart here. So this is the Smith chart, very helpful to us. Let us discuss few of the characteristics corresponding to the Smith chart here. Now the first characteristic with respect to the Smith chart is that the constant R circles and the constant X circles are forming the two families of orthogonal circles we can see here. See, the word orthogonal refers to be of individual type here, and when we see that the crossing between the R and that of the X circles here, if you consider the straight directions at the point of intersection, these are intersecting by the 90 degree of angle. So this is nothing but the orthogonality corresponding to the R and that of the X circles here for resistance and reactances. Or in another words also, if you can see, the resistance is marked onto the horizontal axis, whereas the reactances are marked onto the vertical axis. Next to that, we have again the constant R and the constant X circles that are passing through the point where we have gamma suffix R is equal to 1 and gamma suffix I is equal to 0. So as gamma suffix I is equal to 0, it is neither into the positive half or in the negative half. It is on the central line here, and as 1 is the center, this is the point we have denoted earlier. Next to that, as we discuss, upper half of the diagram represents positive Jx here, x representing the reactance, whereas the negative part represents minus of J times x here. So this is the lower half of the Smith chart here. Now for the admittance, the constant R circles become the constant G circles, and the constant X circles become the susceptance circles represented by small b for the normalized cases and capital B in the general cases here. Now the distance that can be calculated along the Smith chart axis here. So this is the measure of one half cycle. So one half cycle represented as lambda by 2. When you start at 0.0 value here, you go up to 0.25 at the opposite hand here. And when you complete one cycle, so here you come back to the value of 0.49, then 0.5 here. So this is nothing but the half. So one half cycle is completed corresponding to the wavelength onto the Smith chart here. Now at the point where we have the normalized impedance small z is equal to the minimum value obtained by 1 by rho. So this corresponds to that of capital V min onto the Smith chart here. Now at the point of normalized impedance at the maximum level obtained is equal to the SWR itself. So that time it corresponds to the V max value here. Now we know that when we have the maximum of the voltage, so that time we find the minimum of the current. So on to the right hand side we obtain the V max along with I minimum here, whereas when we have V minimum we obtain I maximum here. So now for Z maximum we have rho here, for Z medium we have 1 by rho. So we find V minimum, I max, 1 by rho values onto the left hand portion of the Smith chart here, whereas the Z max, V max, I minimum and the rho values we come to have onto the right hand side corresponding to the center of the Smith chart here. So this was all about the characteristic features with respect to the Smith chart. So when we want to have a switch from the impedance values to that of the admittance value, we have to go for 180 degree out of phase to switch from impedance to the admittance part here. So we have been just now introduced to the Smith chart to determine the fast solutions for the transmission line problems by the method of graphs here. Now in the Smith chart, we can have the measurement of the various patterns. So the various pattern, especially the standing wave pattern, we can say here. So the standing wave pattern we can draw onto the paper with the help of the measurements we go for the Smith chart. There it is another technique into the microwave engineering giving us the same kind of the information but with the help of the practical setup. So in this practical setup we should be having a slotted line here. So slotted line we shall be covering when the microwave components, the passive components especially, we shall be addressing for the subject microwave engineering here. Now either you go with the Smith chart or the slotted line. The standing wave pattern can be determined directly from these two methods, and we shall be having the knowledge of reflection coefficient, the reflected power in turn, the transmitted power also will be calculated when we have the incident power and the reflection coefficient, reflected power, known to us, and also the load impedance. So just now we have talked about its normalized representation for the load impedance or load admittance you can take. So these are the various applications in general we can say for the use of Smith chart here. So I hope the Smith chart introduction is very clear to you people, and now we can carry forward the use of Smith chart to solve two simple problems for transmission line here. So by the next lecture, it will be the problem number 1 based on to the Smith chart here, and we shall be continuing with the same chapter, microwave transmission lines here. So I hope you are definitely getting the subject microwave engineering enjoyed as far as the learning is concerned. For more details, you can subscribe to Ekeeda channel. Thank you.